So the question here asks us to, from 2.4 question 4, asks us to find the roots of z to the 5 equals minus 1 using Demoivre's theorem. So obviously the first one is a real solution, and you can find that straight away without using Demoivre's theorem, which is that z is equal to minus 1, because minus 1 to the 5 is equal to minus 1. Then of course from there we can use our next rule. You can use Demoivre's theorem, or you can simply at that point use your geometrical spacing rule, which is the one I'm likely to use. And so over here you can see that you've got minus 1 being your first solution, which is on the x-axis in the quadrant, negative quadrants I should say, and then because there's 5 roots, there's equal spacing. So you've got 2 there and 2 there. Again, they have to be in complex conjugate pairs because there is only real coefficients, and we know that the angle between all of the subsequent angles is 2 pi on 5, because that is the rule about how complex roots of unity rotate around the axis. So they're all 2 pi on 5 apart, dividing a revolution 2 pi up into 5 places. And from there you need to be a bit careful on this one, because the angles are going from the negative quadrant rather than from the positive x-axis. So normally we would just have cis 2 pi on 5 and cis 4 pi on 5, but in fact, because it's rotating from the negative side, you've got on this diagram here, the one we found there was Z1, and so if you're going to go around in order, you need to be careful about the way you list the arguments. So it doesn't matter which way you do it. I'm going to do them in pairs so that I get Z2 being this one over here, and because that's 4 pi on 5 from the negative axis, it's actually just pi on 5 from the positive x-axis. And because the modulus is still 1, you get cis pi on 5. And because they go in complex conjugate pairs, Z3 down here is cis minus pi on 5. Over here I'm going to get Z4, Z4 being equal to now pi on 5 to Z2 plus an additional 2 pi on 5, which means we get cis 3 pi on 5 for that one, and Z5 being the one in the third quadrant. You can either go to cis, that's 7 pi on 5, but that's the same thing as cis minus 3 pi on 5. That's, I've said that wrong, so that would have been pi, 3 pi, 5 pi, 7 pi. Yeah, no, that's actually right. So what I said is right. So 7 pi on 5, which is the same thing as minus 3 pi on 5. Either way, you know it's going to be cis minus 3 pi on 5 because of the conjugate pairs for Z4 and Z5. Okay, so there's your 5 roots, and grouping them together because of the complex conjugate pairs, the first one is going to be Z plus 1 because it's real. And so Z to the 5, Z to the 5 plus 1. The original statement is Z5 equals negative 1, but if we rewrite that to factorise it, then we rewrite it as Z to the 5 plus 1, because it's an expression then rather than an equation. Well, Z to the 5 plus 1 equals 0 makes it an equation. So Z bar equals the modulus squared, so mod z squared. Now twice real z in these two brackets we've got here, real z is cos 2 pi on 5, so yeah, we get twice cos pi on 5, and mod z is 1, so mod z squared is 1, and that means that the summary of those brackets is equal to z squared minus 2 cos pi on 5 z plus 1, which you'll observe is the middle bracket in the question. Okay, so similarly the last two brackets can be expanded as well, so that z minus cis 3 pi on 5 z minus cis minus 3 pi on 5 actually expands out to give z squared minus 2 cos 3 pi on 5 z plus 1, and then we put it in the format they're looking for, which is z to the 5 plus 1 is equal to z plus 1 z squared minus 2z cos pi on 5 plus 1 z squared minus 2z cos 3 pi on 5 plus 1 as required by the solution.